Okay, great. Okay, so I'm going to start with an introductory lecture. So I'll apologize in advance. Some of the information is fairly basic, but I wanted to make sure that everyone has a common platform for the material moving forward, and there are a lot of small messages that will seed messages and topics that we'll be discussing later this week. And hopefully over the course of the week, you'll meet all of the folks that are involved in putting this event together. So I'll begin with some teaching objectives. The first thing I want to discuss is light propagation across spatial scales. They're intrinsic spatial scales in biological systems, and it's important to understand how those spatial scales interact with characteristic spatial scales that govern light propagation in biological tissues. And it's really understanding both the spatial scales that are pertinent in your application and the optical processes that occur over those spatial scales that will then govern the approach that you will take to model light transport in your system. And there are a variety of models to do that. So once you say you've analyzed your problem, you've actually solved for the light distribution in your system, it turns out that whether you're primarily interested in a therapeutic application versus a diagnostic application, how you will utilize that solution will be slightly different. Obviously, when you're doing therapy, you're very interested in the volumetric distribution of light in that material. Whereas when you're doing diagnostics, unless you have an indwelling fiber optic probe in your volume, you're limited to looking at what comes out on surfaces. And so how you actually mathematically quantify or figure out doses versus, say, reflected or transmitted light signals are different, and we'll talk about how we do that. Then we'll focus for a bit on looking at light transport from light propagation from a transport perspective, where we kind of ignore for the moment the wave properties of light and treat light as the propagation of a neutral particle. And in that context, the fundamental metric that is of importance in characterizing light transport is something called the radiance. It's, in the most general case, it's a six-dimensional object, because light at any location in a turbid media, in order to describe it, you need to first define your location in space, which is 3 dimensions. You have to look at which direction light is emanating from that point, so you have 2 directions. And then you also have time variations if you have a temporally varying source. So the general solution of the radiative transport equation, which is used to predict the radiance, is actually something that lies in a 6-dimensional space. And then we'll take a break from that. We'll return to that later. And we'll shift gears and talk a little bit about, actually, I'm not shifting gears yet. Once we understand the radiance, we'll talk about how absorption and scattering perturb or affect light transport within turbid media, and how that leads to the radiative transport equation, which when one solves, one obtains the radiance. We'll talk about how absorption and scattering affect light propagation separately, and then the RTE actually is a way of treating them simultaneously, because obviously those processes occur simultaneously within tissue. Then we'll change gears and talk more about optical properties, so and where they come from in tissue, both absorption and scattering. We'll also talk about the spectral dependence of optical scattering and absorption in tissue. And when you then understand kind of the spatial dimensions of optical properties together with the physics of light transport, those two put together will naturally give rise to characteristic spatial and temporal scales. And these are important because if you're using any special illumination or detection schemes that vary in space or time, the spatial scales or the temporal scales in which you send in or detect light are actually governed by this interaction between the optical properties and the fundamental spatial and temporal scales of light transport within that tissue. And so that's very important to understand, and we'll be of great importance as the course evolves. Okay, so just to remind everyone from high school physics, there are two ways of describing light. One is the classical wave description, where we remind ourselves that light is a transverse electromagnetic wave. So you have an electric field oscillation and magnetic field oscillation, which are mutually orthogonal to each other. And both of those are orthogonal to the propagation direction. In biomedical optics, we typically are interested in electromagnetic waves in the interval, typically around 200 nanometers to maybe as far as 10 or 11 microns if you're interested in surgical applications using infrared sources. And then there's also the neutral particle description, where we set aside the wave characteristics of light, and we characterize light as localized massless quanta of energy, which we call photons. And there's a relationship between the energy of a single photon, which is related to Planck's constant multiplied by the frequency of that electromagnetic oscillation, and that frequency, of course, can be parameterized through the speed of light and the wavelength. Okay, so if you have the wavelength of light, you have a sense of what the energy content of a single photon is. It's also important just to remember that the spectral interval that we're interested in is a narrow interval relative to the entire electromagnetic spectrum. So typically we reside in this little narrow spectral window here. And so the spatial scale is interesting. It's about a micron, roughly, or hundreds of nanometers. And there are a lot of biological structures that are naturally have characteristic spatial scales on that scale. If you go to longer wavelengths or less energetic frequencies, we transition from infrared to microwaves and radio waves. If we transition to more energetic waves, we transition from ultraviolet to X-rays, hard X-rays, and gamma rays. And the important thing to recognize is that depending on the energetics of the electromagnetic spectrum, you're actually gaining information about various molecular characteristics of the targets you're looking at. So what's important is that in the visible, roughly, the energy of a single photon is on the order of about 1 electron volt. And if you think about that energy input into a system, essentially what you're doing is that you're exciting electrons in most biomolecules, right? You're populating higher energy levels in various biomolecules. And so when you do spectral measurements, you're actually probing the electronic properties of the biomolecules of your system. And as you go to lower energies or higher wavelengths, as you go from maybe the red into the near infrared, the energies of the photons drop, and actually you're no longer as effective in populating excited electronic energy levels, but you're actually probing vibrational modes of molecules. Okay, and these are very important. So if you have spectral measurements, you're really probing that fundamental molecular contrast in your targets. And of course, if you go to lower energies like microwaves, radio waves, you're looking at rotational characteristics. If you're going to higher energy, you start to probe elements relative to electronic structure and nuclear structure. Okay. So bearing that in mind, it's also important to kind of think about the various spatial scales that one might be interested in probing in biomedical systems. So on one end, we have kind of classical microscopy techniques, which where you form an image based on processes that are dependent on the coherent properties of light. Image formation in classical microscopy is sensitive to processes such as interference, diffraction. They're phase-sensitive techniques, so you're actually very sensitive to the coherent properties of light. And so in that context, you really need to understand light through the classical wave description. And so the here the spatial scales for microscopy, you're sensitive to structures on the order of the wavelength of light. And since these images are formed based on these wave characteristics, if one wants to model, say, a microscopy technique, one needs to consider Maxwell's equations fully. As we look at tissue volumes that are larger, and you start to kind of zoom out and not look at, say, just cellular or subcellular structures, but you're interested in looking at cell organization, cell extracellular matrix interactions, how tissues are formed, which is really a composite of vasculature with extracellular matrix and cells. We start to increase the spatial scales of our interrogation. Light scattering becomes more and more important. Optical coherence tomography is a technique that does leverage the coherent properties of light in order to render images with resolutions on the micron scale at depths of a few hundred microns. But scattering is actually quite important in OCT, and actually OCT takes great lengths to actually reject all of the scattered light and actually only looks at the light that remains coherent after those scattering processes have occurred. These other biophotonic techniques, such as spectral imaging, such as spatial frequency domain imaging, which we've already heard about, diffuse optical scattering and imaging, actually do directly detect scattered light. And often when you're looking at spatial scales on the order of hundreds of microns to millimeters, the light has undergone so much scattering that the coherence properties of light have been lost, meaning that all of the light, say, at a given location have traveled different path lengths so that they don't have the same phase, and therefore they're completely incoherently combining. And in that sense, one can actually dispense with the Maxwell's equations approach and treat light as a neutral particle. We ignore processes such as interference, diffraction, and we treat light in a particle context. And this and the characteristic length scale that governs kind of this the impact of scattering or the impact of light propagation is the mean length between scattering events. And so that's referred to as L sub S. In tissues, that typical length scale is on the order of 10 to 100 micrometers, depending on your tissue. So that means that on average, a photon will travel anywhere from 10 to 100 micrometers before it gets scattered or redirected into a different direction. And that redirection, the magnitude of the redirection is governed by the actual constituents within the tissue that scatter the light. And we'll talk about those characteristics in a bit. After the light is scattered so much such that, say, you initially had light coming from a collimated light source like a laser, after it scatters sufficiently, tens to 100 times, let's just say, to throw a number at it, the photons actually have lost complete memory of the original direction that it was launched. And in that case, you can actually make further approximations that allow you to provide a more simplified solution to the radiative transport equation, which is approximate, which is called the standard diffusion approximation to the radiative transport equation. And those spatial scales are linked to something called the transport mean free path. And that spatial scale is typically about an order of magnitude larger than the single scattering path. So it's on the millimeter spatial scale. Okay. And so this is certainly pertinent when you're looking at optical techniques that interrogate organs. So there are a lot of optical techniques that look at brain imaging, breast imaging, muscle physiology. Typically, in those techniques, you're interrogating volumes of tissue that are tens of millimeters, cubic millimeters. And the light that you're detecting has certainly undergone sufficient interaction with the volume such that the diffusion approximation may provide a sufficient framework in which to interpret your data. So let me just talk about each of these three frameworks individually so that we understand kind of what the merits and demerits of each approach are. So as I mentioned, Maxwell's equations form a rigorous model for electromagnetic wave propagation. It models all wave phenomenon, interference, diffraction, polarization, and it is accurate on all spatial scales. The challenge with applying it to biological systems is that in order to solve the electromagnetic equations, the Maxwell's equations, you need to know the properties that govern electric and magnetic wave propagation, and these are known as the dielectric permeability and permittivity. And actually accessing relevant values for those properties for tissue systems is very difficult. Moreover, it's often understood that those values are actually varying spatially continuously within tissue. So often the application of Maxwell's equations to describe light transport within tissues is compromised in part by our ability to accurately represent computationally what a tissue looks like from a Maxwell's equations perspective. Nonetheless, there's been some important work in trying to understand primarily microscopy type of techniques in turbid tissues using a Maxwell's equations approach. I would say that the pioneers and leaders in this field are Vadim Bachman at Northwestern University and Andrew Dunn at UT Austin. They've developed finite difference time domain and pseudospectral domain methods to solve Maxwell's equations. And the tissue volumes that they're able to consider are still fairly small, cell and cell aggregates, maybe no more than volumes that are maybe 50 microns, cubic microns on each end. So very small, and they take literally thousands of hours to solve because of the computational expense. And so Janneke will be talking about these topics later this afternoon, and we're working on some approaches that we feel have, that we know actually have reduced the computational burden by orders of magnitude that may start to give us more insight as to how biological tissues modify, how the scattering in biological tissues modify the propagation of focus beams. And that's quite relevant to all these nonlinear microscopy techniques that are emerging in biomedical optics, like multiphoton microscopy, second harmonic generation, where you're actually producing very high resolution images at modest depths within tissue. And so understanding that is quite important. As the light propagates and starts to scatter, there may come a spatial domain where we've lost information on the directionality of the light. We've lost information with respect to the interference and diffraction of light because the phase relationships have been scrambled. And in that context, one can adopt the radiative transport framework, which treats light propagation as the transport of photons. And interestingly, the radiative transport equation can be derived from Maxwell's equations under certain limiting assumptions. The first thing is the treatment of scattering in a radiative transport context. And one thing that one has to understand is that in radiative transport, we have particles that are responsible for the scattering of light. And each particle, if you look at the electromagnetic wave or the photons that are impinging on a particle, which then scatter the photons, every particle has to be receiving photons that have propagated a sufficient distance from other particles that may have emitted those photons. And so each particle has to lie in what's called the electromagnetic far field from scattered waves produced by other particles. And the reason for that is that if you look at scattered waves from particles in the Maxwell's equation context, the angular distribution of that wave actually evolves after it is scattered by that particle. And then it reaches a far field and kind of non-evolving angular distribution. And that's typically on the order of 6 to 10 particle diameters. So if you have, so the radiative transport equation uses a very simplified approach for characterizing the angular distribution of scattering. In order for that to hold, you have to assume that each scatterer lies in the electromagnetic far field of all the other scatterers. And the other thing that we have to assume is that there are no correlations between particle positions, because if you have correlations in particle positions that are, say, spaced at some multiple of wavelengths of light, then you will preserve the optical phase relationships over large distances. And therefore, coherence can be maintained over long distances. And that cannot be handled properly in a radiative transport context. Interestingly, so this is a scalar model. It can predict interference and diffraction effects. And so we've got to make sure that there's no correlations in that sense. We can handle polarization using a transport equation for what's known as Stokes vector. So Stokes vector is a construct that allows you to characterize fully the polarization state of light. And it's a 4-element vector, and you can essentially write 4 radiative transport equations that characterize the propagation of each of these polarization components in the Stokes vector. Okay. So the spatial scale kind of a rule of thumb for where one can dispense with the electromagnetic wave, the Maxwell's Equations framework, and adopt a radiative transport equation framework is probably on the order of a few hundred microns, okay, to be sure that your optical phase relationships are no longer pertinent. Now, if you then look at biological systems where your characteristic spatial scales are on the order of millimeters, the light scattering that the photons experience are so extensive that you start to blur the angular distribution of light because you have so much scattering dispersion. And so in that case, you can actually make further approximations to this radiance. We talked about the radiance within the radiative transport context, which is a complete description of the spatial and angular distribution of light. And you can make an approximation, or you can approximate the angular distribution of light using Legendre polynomials, which is a subset of spherical harmonics that assume azimuthal symmetry. So what you do is that you assume that the radiance, the angular distribution of the radiance, can be approximated by a summation of Legendre polynomials of higher order up to some arbitrary order n. Okay, and so you can do what's called a P1 approximation, or a P3 approximation, or a P5 approximation, where P refers to the Legendre polynomials and n is the order. And where you terminate that series of Legendre polynomials basically results in an n+1 system of coupled partial differential equations, which can be solved with some difficulty, but still can be solved. In the field of diffuse optics, actually, the simplest approximation, the P1 approximation, which in a spatially, temporally invariant system is the same thing as the standard diffusion approximation, has a long history in biophotonics. The first applications of using light to probe brain, breast, and muscle physiology all relied on the standard diffusion approximation. And essentially, it makes the simplest assumption on the angular distribution of light in the tissue. Basically, it's essentially an isotropic term, meaning light is moving equally in all directions, plus a cosine term, which actually gives you some directionality. And this approximation can be accurate when you have a medium where scattering is much more dominant over absorption, and we'll talk about how much more dominant it needs to be, and at locations that are far away from your optical sources and boundaries. And the reason why that's the case is that if you have a laser source, obviously, the light is highly directional. It's basically you have almost a delta function in one direction and nothing everywhere else. And if you're going to try and model that light distribution using just a few Legendre polynomials, you're going to fail badly. The other thing is that at a boundary, so say the tissue-air interface, you have a refractive index mismatch. And light gets redistributed based on the Fresnel relations, right? When you have light trying to pass from a medium from one refractive index to the other, and the angles get redistributed in a way that is not well captured using, say, a P1 approximation. So one has to be mindful of that. Okay. So I sometimes find this graph helpful to kind of, again, bear in mind applications and spatial scales. So this is kind of a resolution or image resolution of various optical techniques on the vertical axis and the depth that can be accessed by various applications. And so kind of in the lower left-hand corner, you're really probing systems on spatial scales similar to the wavelength of light, and you really need to think about coherence and Maxwell's equations. So you have kind of the standard microscopy methods, confocal microscopy, multiphoton microscopy, and OCT. Now, once you go to spectral imaging, spatial frequency domain imaging, diffuse optical tomography, you start to collect light that have been more and more dispersed by scattering. And so modeling techniques in kind of this interfacial region, you need to really consider Monte Carlo, because you're in this domain where the transport of light cannot be dealt with in a kind of an isotropic or in a diffuse way. But when you're looking at much larger volumes of tissue at much larger depths, dealing with the diffusion approximation can be quite useful. Okay. So I think I want to pause there because we've talked about these three very different ways of handling light transport, and I'm going to move towards trying to focus for a moment on the transport context and look at the various considerations for dealing with therapeutic applications versus diagnostic applications. So before we do that, why don't we just take a break for questions? Any questions? I've got a microphone. So is everyone fully comfortable with kind of understanding in what situations one might need to use Maxwell's equations, or one might be able to get away with a Monte Carlo or a radiative transport solver, and also when one maybe must use a radiative transport equation solver like Monte Carlo, or one can get away with an analytic approximation such as standard diffusion? Because those choices are sometimes difficult to understand conceptually, if not practically. Yeah.
So I was wondering with the radiative transport equation,
yes.
You said that it assumes that you have this relatively far field of scattering. So how would you attempt to go about, solving for the light distribution in a highly scattering medium that you maybe can't assume that the scattering is in the far field?
Okay, so the easy answer to that question, which is easy to answer but hard to implement, is that you would have to use Maxwell's equations. Okay. But I think there's also a more subtle way you can address that question, and that is ultimately when you solve radiative transport, you assume a certain set of optical properties. Mm-hmm. And those optical properties are in some sense derived from a self-consistent framework where you know that either using Monte Carlo simulations or even in the old days using diffusion approximations, say you excise a piece of tissue, you look at the transmittance and the reflectance, and by doing that you can make certain computations. If you know the thickness of that tissue, mm-hmm. you can extract your absorption and scattering properties. And if you do even more sophisticated measurements where you actually take a very thin slab of tissue and you look at the angular dispersion, you can characterize the phase movement. Mm-hmm. So in that sense, you create effective scattering properties of your tissue which treat the tissue, even though it may be composed of scatterers that don't necessarily lie in the far field of each other. Mm-hmm. You have come up with a robust characterization within the radiative transport framework. The only caveat to that is that if you have a system where not only do you have scatterers that do not lie in the far field of each other, but there is spatial organization on spatial scales similar to the wavelength of light. You can have coherent propagation of light. And therefore, the radiative transport equation is going to give you garbage. A potential example of that is if you look at tendon, for instance, they're highly aligned collagen fibers, and probably transport of light along collagen fibers may have some light channeling effects. Radiative transport is not going to treat that very well. So this may be also an opportunity to probe what Dr. Spanier may have to say on that topic, right? So, and maybe I should just say that my comments on the radiative transport equation with respect to the far field is that that's how you can rigorously derive RTE from Maxwell's equations, okay? But you can also just adopt the radiative transport equation as an ansatz and say, okay, within this framework, this is how I'm going to treat absorption and scattering. Okay.
Well, if you have an essential need to treat the coherence of light in some locations, but you prefer to use radiative transport for obvious reasons, it's cheaper, it's faster, you might try a hybrid computational method. We've experimented a little bit with that here, in which you begin with Maxwell's equations, but cut them off, switch to radiative transport after you've achieved a certain goal, which I won't try to define here because it's kind of nebulous, but that would be a way of taking advantage of accuracy near in and speed and adequate description of the light in the far field of those particles. So that's a possibility. I don't think a lot of work has been done on that combination.
Other questions? Good.
So you spoke about the P1 approximation, which is a more simplified diffusion approximation. Mm-hmm. So if you use some higher order approximation in PN, how would that benefit? Like, would it help for certain cases where the P1 approximation is failing?
Yeah. So yes. So how does it help? So as I mentioned, in radiative transport, the way you characterize light is using this thing called the radiance, which we're going to talk about very soon, and that characterizes the angular distribution of light that is impinging at a given point. And I just use this simple kind of illustration that obviously the most extreme structure that one can have in angle is having a collimated light source, because if you plot, say, the intensity of light on the y-axis and angle on the x-axis, call this theta, right? A laser source essentially is a delta function here, right? And it's zero everywhere else, okay? And so in order to, let me just do something like this, right? So in order to model that, and so the light field, obviously, if you're sending this into a tissue, you can imagine that very close to the source, you have a very, very strong and narrow peak of light in theta. Now, if you're trying to model that with the first two Legendre polynomials, which we'll talk about later, the first Legendre polynomial in theta is this. Okay? The second Legendre polynomial in theta is this. So you're not going to do a very good job. But as you go to higher Legendre polynomials, it's kind of like, I think probably people remember Fourier analysis from undergraduate physics, and they show if you want to model a square wave, how many Fourier components do you need in order to map that square wave? And you see that as you go to higher and higher order, you're able to map that square wave, but you still get these oscillations, right? So if you have a square wave, you have this. And then if you say, I'm just pulling a number, you say, once you go to, say, the first 5, you have something like this. It looks something like this. And this is the same concept in PN, only it's on the unit sphere and it's characterizing the angular distribution. So the higher order moments, when you go to P5, P7, P9, you're going to be able to model or capture highly localized angular distributions much more effectively. Okay, does that address your question?
That looks.
Other questions? Okay. Please raise your hand if you have questions, and because if a question is arising in your mind, I'm sure it's arising in others. Okay, so let's talk about therapy versus diagnostics. And I have these new fancy, well, not new anymore, but there was this time when green laser pointers were really cool, but that was about 10 years ago. They used to be all red, right? But now I can't do this beautiful experiment where if I had a red laser pointer and I shined on my finger, my whole finger would be glowing red. But now with green, forget it. I can't do that. But everybody's done that, I'm sure. You aim a red laser pointer on your finger and your whole finger glows red. Okay, and so if you think about taking the cross section of my finger, you can imagine that the red comes in and you get some distribution of light in your finger. It doesn't go directly through, and you have a laser coming out the other end of your finger, a laser beam coming out the end of your finger. You have some lateral dispersion, and you have some attenuation, right? And this internal light field within the volume of your finger is what's relevant if you're interested in, I think someone talked about doing photodynamic therapy, if you're doing photothermal therapy, even if you're trying to excite fluorescence, right? If you're trying to excite fluorescence, you're very interested in what is the volumetric distribution of the light, because that's going to tell you how much fluorescent light you're capable of generating, okay? So the way to measure the total amount of light that is resident at any point, the metric that we use for that is called the fluence rate. We typically use the Greek letter phi. And just if you're looking along this central point, rho or x equals 0 and z, you're going to have some decay of that fluence rate, right? Because obviously you're losing light due to scattering, and you also have some absorption due to biomolecules in your tissue. And so you're very interested in the spatial distribution because that's going to tell you, how effectively are you going to be able to generate fluorescence here versus here, or how much is your temperature rise going to be here versus here. Okay, so that's what's important for therapy or fluorescence excitation. Now for diagnostics, you don't have access to this directly. You only have access to what's coming out either the other end, if you happen to be working in a very thin tissue system, or you can only look at the stuff coming out back through the surface. So this is a top view. This is what your distribution may look like. This is light that's entered the tissue and multiply scattered and come back out. Here, there's some sort of decay in the radial direction or on the surface. So this is the surface depiction. And you can measure this either in reflectance or in transmission. And so you're limited to the light signals measured at the tissue boundaries. And so, so the radiative transport equation, or Maxwell's equations, you have to define your tissue. We talked about problem definition. So say I am able to construct this geometry and relevant optical properties, and I come up with a solution. The solution will actually give me the distribution of light, either electric field intensity or radiance within this tissue. And I need to I need to actually either compute the fluence rate or I need to compute the reflectance or transmittance. And the question is, how do I do that? And so that's something we'll address in a moment. But ultimately, I want to first understand how does this light field get formed, just conceptually. So let's just think about if a photon in a radiative transport context enters a system which is composed of scatters, absorbers, and potentially fluorophores, what are the potential trajectories that a photon can take of many trajectories? So the first thing is that if there's a refractive index mismatch between the tissue and the surrounding air, some of the light won't even get in because there's a specular reflection. And sometimes we take pains to make sure we don't detect that because that doesn't give us any information about the interior of the tissue. If the light enters, it can undergo one or multiple scattering events and get re-emitted. And that's something we call in our field diffuse reflection or diffuse reflectance, although the photon doesn't necessarily need to be fully diffused in the sense that it doesn't necessarily have to lose complete memory of its initial direction. You can actually have a photon that gets absorbed and gives rise to, say, any set of processes. I just said that, say, results in a temperature rise, for instance. You can have light that gets transmitted after undergoing some number of scattering events or going directly through. Or you can also have an absorbing event that gives rise to fluorescence. Okay? Of course, fluorescence will result in the emission of light at a different wavelength. Okay? So typically in this class, we will not focus on transition in energy. In some sense, when you put in light at one wavelength and you get light out at a different wavelength, you're basically transitioning from one energy to the other. And we're going to restrict our consideration to what's called a single energy or a mono energy equation. Okay. So the global light balance, so all of this light that you send into the tissue essentially has to go into one of these four outcomes: specular reflectance, diffuse reflectance, absorption, or transmission. Okay. So it's just an energy balance. And if you imagine after you have, in a Monte Carlo simulation, for instance, done trials of thousands, if not millions of photons, you can imagine that some sort of light field is built up that looks something like that. Of course, it's three-dimensional. This is just a 2D cross-section. And at any given point, the solution to the radiative transport equation will give you the total angular distribution of light that is emanating from that point. Okay? This is just a two-dimensional cross-section. It's actually something that resides on the unit sphere. And you can just imagine conceptually that obviously since you have a collimated source coming in here, you're more likely to have more light traveling forward, and then you have some light that is being scattered laterally, and then you also have some light coming back from scatters that are backscattering. Okay? And this full description in space, angle, and time is called the radiance. It has units of power, which in some sense is photons per second, right? Each photon has energy, and energy per unit time is watts, so photons per second. It has units of per area, because you have to do a cross-section of that small point. So you have a cross-sectional area, and units of steradians, which is a unit of solid angle. And we'll talk about how you compute solid angles. But the basic concept is that if you think about a unit sphere, the surface area of a unit sphere is 4 pi, right? And so if you're looking at some subset of angles emanating from a point, then you're going to have steradians that are less than 4 pi, right? So, so you have to look at how much energy you're actually emitting for a certain cone of light. So in order to solve for this radiance, that's what the radiative transport equation or a Monte Carlo simulation gives us, we need to figure out how to treat scattering and absorption simultaneously within the medium. So let's just first talk about the effects of absorption and scattering separately. So first, if you imagine that you have a very, very small differential slab that consists of no scattering but some absorber, And you have a radiance that is impinging at location S. So this is a one-dimensional object. So you have location S. And all the light is traveling in a given direction, omega. So all of the light is traveling only in one direction, kind of like this direct delta function. The light that will be coming out the other side will also be pointed in that same direction because there's no scattering. There's no way to redistribute the direction. And most likely the intensity of that light will be reduced because you have some amount of absorption in this slab. So the drop of, or the change in the radiance per unit distance, ds, is linked to some amount of absorption, which we'll call mu sub a, it's called the absorption coefficient, times the amount of light coming in, okay? And the negative sign is because you know that the amount of light is dropping, okay? So if you just do separation of variables, you get dl over L is equal to minus mu a ds, and you integrate that, you get the classical Beer-Lambert law, that the radiance as a function of some coordinate s traveling in this one direction omega is given by some incident radiance with an exponential decay of mu a times s, where s is your coordinate, okay? The key thing here is that once you get absorbed, the photons no longer propagate, so they terminate, okay? So this is classical Beer's law. It's something that you're all familiar with. Now the situation is in some sense similar for scattering, but also a bit different. So we can set up the same slab. Now we've replaced the absorber with a scatterer. And these photons are impinging in one direction on this target. And if you're looking at the radiance only in the one direction of the incident light, you're also going to get some sort of decay, right? You're going to get some loss. You may have light that gets scattered and gets transmitted, but it will get transmitted in different directions due to scattering. And so you're losing light from that one direction. So you have a similar expression. You have the derivative of the radiance with distance. You have some loss depending on the scattering coefficient of that target multiplied by the radiance that's available. And you get this modified, you have basically a Beer's law for scattering. But again, you're only considering that one direction. The key thing, though, is that the photons are not completely lost in the scattering process, right? They're just now propagating in other directions. And in a three-dimensional system, you still have to account for those, okay? If you want to think about total attenuation of light along a ray, you are basically losing light due to both absorption and scattering, and you can have an attenuation due to the sum of absorption and scattering, which we call mu t. It's the total interaction coefficient. Both mu a and mu s have units of inverse distance. It's basically the number of absorption or scattering events that you will have per unit length of propagation. So if something has a scattering coefficient of 10 per millimeter, it means that on average, when a photon travels a millimeter, it will on average undergo 10 scattering events, okay? Okay. So now the question is, how do you combine these simultaneously? And that's what the radiator transport equation does. And so perhaps some of you are familiar with this equation. Some of you, I'm sure, perhaps are not. I know that when I first looked at this equation, I got really scared. And so it took me a while to at least understand this. And so first, I just want to give you a conceptual understanding of what each of these terms in this equation means. It's actually conceptually very simple, but it's just very meticulous in conserving energy in the system. So the first term here on the left-hand side is the time derivative of the radiance, because in general you can have a source that is changing with time. And so if I look at one location R in your three-dimensional system, and you consider light only in one direction, omega, I want to see, okay, at that one location, in that one direction, how much is my light changing in time, okay? I've multiplied this by 1 over v, which is the velocity of light in the system, mostly just for compactness. Perhaps a better way of writing this is actually putting the velocity in front of each of these terms here, because this is a rate. So photons are never stationary, they're always moving. And so all of these are rates, and the rate is given by the speed of light. Okay, so the question is, what can contribute to the time rate of change of light at a given position at a given location? Well, the first thing is that light is moving, right? And so light is always propagating. If I'm looking at one location, say on the 405 freeway, the cars are always streaming by, right? And so this term, and there may be areas on the freeway that are more congested than other areas where the cars may be spaced further apart. So what I'm interested in is that how is the density of photons changing with space? And that's what the gradient operator gives you. It gives you the variation in space of the number of photons. And now I'm not interested in the global variation. I'm only interested in the variation along the direction I'm considering. So I want to take the dot product of this general gradient operator and project it along omega, because we're only interested in how light is changing along that one direction omega. Okay? And you're losing light, right? Because light is being emitted from that location. You want to see, and the rate at which that's happening is actually the velocity times this. Okay? So this is basically loss due to streaming or loss due to propagation. Okay? The other thing that may happen at that location is that you may lose light due to absorption or scattering. The absorbed light is lost. The scattered light is also lost. It's lost from that direction omega. It gets propagated into a different direction, but from the perspective of this omega, the light is gone. Okay? Now you have opportunities to gain light. Well, there could be light that comes to this point from another direction omega prime that undergoes a scattering event and then gets scattered into the direction that you're considering, omega. And that's what this integral does. So what does this integral do? First it says, okay, how much scattering do you have in that location? Okay, so that's mu s. Okay, so that gives you some sort of magnitude of how much scattering you have. Now what I want to see is that, well, how much light do I have in all these other directions omega prime? And I want to multiply that amount of light by the probability that light can get scattered from these other directions omega prime into direction omega. Okay? And then I want to integrate that over all possible directions omega prime. And all other directions omega prime are all the angles that lie on the unit sphere. And this is an integration over all directions. And 4 pi just tells you, well, reminds you this is an integration over a unit sphere, which has a surface area of 4 pi. Okay? So this basically tells you how much light can I gain in direction omega due to scattering from light that resides from all other directions. And so you've got to multiply the light traveling in all other directions by the probability that light can get scattered at that location R into the direction that you're interested in. This is something that you may be familiar with called the single scattering phase function. Okay, it characterizes the angular distribution of scattering by a particle. And then, of course, you can have some sort of source of light within your volume, and that has some characteristics in space, time, and angle. Okay, so let me pause there just to open up for questions, and I'm also going to turn off my screensaver, which is making maybe that was not a good choice. Okay, here we go. Turn off my screensaver so the screen doesn't go blank. There we go. Okay, questions about the radiative transport equation? Don't be shy.
So just for that last source term, the radiative transport equation, that's so if your spatial location is inside the tissue volume, that would be a source actually inside the tissue, such as from fluorescence, rather than a source at the surface of the tissue.
Okay. So so if you have a source coming from the outside of the tissue, it induces a source within the tissue, right? Because typically, as you know, if you enter the tissue, the different photons may propagate different distances before it actually first interacts with the tissue, right? Because you have this mean path for scattering or this mean path for absorption. So typically, even an external light source actually induces a volumetric distribution of light within the tissue. And that's how it's treated within the radiative transport equation. Does that answer your question?
Yeah.
Yeah.
Just to make sure, this is only applicable to the mesoscale, right?
Right, so this is in the transport context. So this is not in the Maxwell's equations context. So we're assuming that coherence is not relevant here. You don't have phase relationships that are maintained. So this is all in the transport particle context of light propagation.
Okay.
Any other questions? Okay. So just a reminder here, so L is the radiance, V is the speed of propagation, mu t is this total interaction coefficient. It's the sum of absorption and scattering coefficients. Mu s is the single scattering coefficient. P is the single scattering phase function, and Q is your source. And so these are your nomenclature here. Okay. So I alluded to the fact that radiative transport, even though it can't model interference and diffraction coherence, it can treat polarization, because often there are technologies that look at sending light in with a given polarization and looking at the depolarization or modifications of polarization, because that can give you some information regarding scatter size or scatter density. And this can be treated within the radiative transport context using something called the Stokes vector, which collectively gives you a comprehensive description of the polarization state of light. So you have parallel components of the electric field, perpendicular components of the electric field. Star refers to the complex conjugate of that. So the radiance is replaced by the Stokes vector I, which is now a 4-component vector. And the other thing that changes here is that the phase function is replaced by Z, which is a scattering matrix, which tells you how a scattering or interaction of an electric of light of various polarization states may basically deplete one component of the Stokes vector and repopulate other components of the Stokes vector. So this becomes a 4x4 matrix instead of just a single function as a function of angle. Okay. Okay, so now we get to kind of, with that background in the radiative transport equation, let's assume for the moment that we've solved the radiative transport equation for this system. And again, if you're in a therapeutic context, you're not necessarily interested in the radiance, you're interested in the fluence rate. You're interested in what is the total amount of light that's emanating or impinging at a given point. So within the material, you want to integrate all of the stuff that's emanating from the point, and that's the fluence rate, phi. It is not a function of direction because you've now captured all of the direction. It's only a function of space and time. And it is basically an integral over unit sphere of the radiance over all angle. Okay? So how do you do that integration? Well, let's just remind ourselves about spherical coordinates. So if you adopt a system where the z-axis is vertical and the xy axis is the horizontal plane, any location on the unit sphere is dictated by two angles, the polar angle theta and the azimuthal angle phi. So the way I think of it is theta equals 0 is looking directly up above, theta of 90 is kind of looking at the horizon, and theta of 180 is looking into the floor. Okay? Phi is looking basically along the horizon, right? So you can look in all directions, right? So phi goes 360, but theta goes from 0 to 180 or 0 to pi, okay? So since the radiance varies with phi, with omega, we need to do a integral of the radiance for each kind of infinitesimal surface area along the unit sphere. The way that you can decompose d omega is using spherical coordinates. You think that this infinitesimal patch on the unit sphere, the area of that is given by this arc here is given by delta theta, is just the portion of the circumference of a unit circle, okay? And this arc here, the azimuthal arc, is given by sine theta, which is the distance of this patch of the unit sphere from the z-axis, times d phi, which is the amount that you're varying in the azimuthal angle. So the theta, which is the polar angle, looking up versus the horizon versus down, that integral goes from 0 to pi, or 0 to 180 degrees. And for each theta, you have to make the full loop around the z-axis. So the phi goes from 0 to 2 pi. Okay? So once you do that integral, if you have a functional description of L with respect to omega, you can do that integral and you'll get the fluence rate. Now, things become a little different when you're looking at reflectance or transmittance, okay? So again, let's look at, we have the same object here. We've characterized the radiance within the material. So that means we'll have a solution for the radiance just below this boundary. I'll call it z equals 0, but z equals 0 plus something, just an infinitesimal point here. Below the surface, you have a description for that, but you're really interested in what's coming outside. Well, one has to make a transition from the light field inside the material to outside. I won't discuss that transition right now. We will later on. But there's some sort of mapping of if there's a refractive index mismatch between the target and the outside, you're going to have to deal with Fresnel reflectance here. You have to deal with some boundary condition here. And that will give you a distribution of light that is emanating from this point R at z equals 0, but just outside the surface. And I call that z equals 0 minus because this is the target is in the positive z domain. The air is in the negative z domain. So let's pretend that we have that through the appropriate application of a boundary condition. To be able to figure out the reflectance, which is all of the light that is escaping, we need to integrate this only not over the whole unit sphere, but just over a unit hemisphere that is facing above. So in this case, it's all angles where the direction of light, which is given by these yellow arrows, dotted with the inward pointing normal z vector, where that dot product is less than 0, right? So if you take the dot product of this angle, this arrow, with the inward pointing normal vector, you're going to get a negative because it's obviously the vertical component of this direction is actually pointing outwards, okay? So you want to look at all directions omega, which are outward pointing, That's what this omega dot z less than 0 means. You're not integrating over the whole unit sphere, just in that half sphere. You're looking at the distribution of light that's emanating from this one point in angle. And we need to project that onto the outward pointing normal. So you have to take the direction of light that is being propagated out, and you want to project that onto the outward pointing normal, which is negative z. Okay? And then you can do the same tricks for decomposing the sphere, the omega into sine theta, d theta, d phi in the same way. Okay. So let me pause here just to make sure this got a little mathy. Just want to make sure you're okay with the spherical coordinates. You're okay with the projections, the dot products. Don't be shy, because I remember struggling with this myself for a long, long time. Come on.
So for absorbance, it would kind of be, you just have to do the reverse, I guess, like just change it up a little bit.
For absorbance.
Like
So,
going into the medium, whatever.
The absorbance locally or on the...
So you're calculating the light emitted from a given location. So to calculate the light, like going into, like z in the positive direction, would you just change the variables?
So the light going in some sense, is transmission.
Oh, transmission, yeah. Sorry.
Right. Okay. So yeah, if we're interested in transmission, so let's look at slab, right? Okay. So we have light going here, generates some light field, whatever. And then you have some distribution of radiance. So you're going to have some, I'm just going to be abstract here, right? You have some light coming out here. I'll keep the same coordinate system here, z, right? This is some, I'll call this z equals capital T for the thickness of the slab, right? So you would just do an integral over z dot omega. Here it's greater than 0, right? Because you have to be outward, you have to be pointing outward. And then you'll have the radiance, L, are evaluated at some z equals t plus, because you want to be on the opposite side. We've accounted for whatever the magic the boundary does. Omega t. And then we've got it now projected on the outward point of normal. So the minus z dot omega will just be z dot omega.
Okay.
And then you have the same thing, sine theta, d theta.
Okay.
Yeah? Other questions? I'll just say, personally, the first time I had to really delve into these equations was when I was doing experiments where I was actually looking at an interstitial source in a big vat of intralipid. I'm sure people have done experiments in intralipid. Many of you have. And I was collecting the light field using an optical fiber, which has a certain narrow aperture. And I was measuring it. So I had one of these cool fibers with a little ball tip. So it was radiating light in all directions. And I was really interested in the effect of collimation in some sense. So I had two experiments. One where I had an optical fiber pointed directly. It had some acceptance angle here. But I also had an optical fiber which was oriented this way, looking down. And you have to do these integrals in order to be able to, and I had a new model which I felt modeled the situation properly, and I had to make sure I got all my dot products correctly, and I wasn't integrating over even a hemisphere. I was integrating over this numerical aperture of 0.37 or something. You know, so you have to be careful about doing these things properly in order to interpret your data correctly, and also to try and match it, make it match a model. Okay. So these equations do have practical importance. Okay. Okay, so now we're going to switch gears. We'll put math mostly aside, not completely, but we're going to shift into a more conceptual part of this lecture. So we're going to talk about tissue scattering and absorption and where it comes from. So this is now a very famous slide in our field, developed by Steve Jacques at Oregon Health and Sciences University in Portland. And here he's trying to communicate the tremendous complexity of cellular and tissue ultrastructure, the spatial scale. So in tissue, we have structures that on the order of tens of nanometers. You have phospholipid bilayers, which comprise cell membranes. You have phospholipid bilayers within cellular organelles. One of which is mitochondria, which is kind of the ATP producer within your tissue. So mitochondria is the cellular organelle, which is on the order of anywhere, say 700 nanometers to 3 microns in characteristic dimension. And so the mitochondria itself can scatter light, and the scatter can be thought of as an ellipsoidal object with characteristic sizes of about a micron. But within the mitochondria, you have all of these various membranous structures, each of which also can scatter light. And so you have clearly origins of scatters, or you have scattering objects that interact with light on different spatial scales. We don't only have cells within tissue, we also have extracellular matrix. The most common protein of your extracellular matrix is collagen, and even collagen has a tremendous diversity of structure and hierarchical structure. On the most zoomed up scale, you have the individual triple helix of the triple collagen molecule, and where these individual helices join and meet, there's a refractive index perturbation that leads to a banding of the collagen molecule that you can see on electron microscopy. You get these striations on the order of 70 nanometers. These striations are actually tightly regulated in many organs, cornea being one of them, because your cornea is perfectly transparent. In order to keep the cornea transparent, you have to really regulate the refractive index variations within the cornea. Of course, these molecules aggregate and form larger structures, such as a ligament or tendon or your skin. And depending on how they aggregate and get put together, they have different levels of translucency. You have collagen fiber bundles, which have various scattering, and the characteristic spatial scales can be on the order of several microns. Okay, and then you've got a whole bunch of different structures, some of which are shown here. What's important here is that these spatial scales are kind of right smack dab in the center of where we're interrogating the system, typically with visible or near infrared light, which has spatial scales on the order of, as you know, 400 nanometers to about a micron, or if we're going into the near IR, and how that electromagnetic wave sees or interacts with the tissue is going to be different depending on whether the spatial organization has structure on this nanometer spatial scale, tens or hundreds of nanometer spatial scale, or you have heterogeneity on the tens of micron spatial scale. And here, these should be lambdas. In this plot, Professor Jacques was saying that, well, if you have targets that are much smaller than the wavelength of light, the intensity of the scattering typically has a wavelength variation which goes as 1 over lambda to the 4th power, or lambda to the minus 4 power. This is commonly referred to as the Rayleigh scattering. It's really the Rayleigh limit of Mie scattering. And then if you have structures that are comparable or larger than the wavelength of light that you're using, you have something closer to what's called Mie scattering, which is where the wavelength dependence is on the order of 1 over lambda. And we'll talk about that a little bit more deeply in just a moment. So let's talk about optical scattering just more abstractly, more fundamentally. Again, if you want to characterize the way that a particle scatters light, you have to go to Maxwell's equations. And this is a basic depiction of that. So Mie scattering deals with this, addresses the simple problem of a electromagnetic plane wave of a given polarization state. So you can have a polarization state that's a mixture of parallel and perpendicular polarization that propagates and impinges on a particle of an arbitrary shape and size. This will give rise to a scattered wave, also possessing perpendicular and parallel polarization states, whose intensity will vary with both angles theta and phi. Okay? And that mapping from an incident electric field, so this is your parallel and perpendicular components of your electric field that are incident on this particle, it gets transformed by the scattering characteristics of this particle. So this is called the scattering amplitude matrix. It tells you how parallel incident light can give rise to either parallel scattered light or perpendicular scattered light, or parallel polarization and perpendicular polarization components of the scattered light, and how that varies with theta and phi. And similarly, it tells you how the perpendicular component of the polarization of that electric field, incident electric field, can populate parallel or perpendicular polarization components of your scattered wave. And this just refers to the propagation and the evolution of a spherical wave. This is the attenuation with distance. K is your wave vector, and this is your attenuation. This is the phase accumulation. So the scattering amplitude matrix is the fundamental and the most comprehensive description of how this particle scatters light. Okay? And it is given to you by the solutions to Maxwell's equation for this system. Okay? We typically don't do this computation unless you're doing a rigorous electromagnetic solver. We look at more simple descriptors of this scattering amplitude matrix. The most common one that most of us is familiar with is mu s. Mu s is the scattering coefficient, but the mu s doesn't appear, is actually related to the scattering amplitude matrix, which I'm going to talk to you through something called the scattering cross-section. So let's just imagine a simple case where you have a planar wave incident on a particle, and you have a detector that is resident at a location directly opposite. So this incident light on the scatterer will give rise to a scattered wave, and the single scattering cross-section has units of area, and conceptually it represents the area of a perfectly absorbing and index-matched disk necessary to produce the measured reduction of light. So this detector is not going to capture I naught. It will most likely capture something that is less than I naught. And the question is that if I replace this scatterer with this perfectly absorbing and index-matched disk, it has to be index-matched because we don't want the disk to produce any scattering, how large would that disk have to be in order to produce the measured reduction in scattering, in intensity? Okay, and that's what sigma s, and it can be calculated by looking at the ratio of the scattered wave, the intensity of the scattered wave, over the incident wave, and you integrate that over all directions, and that's the single scattering cross-section. It can be expressed as some effective area, the area of the particle itself, projected onto the detector, times the scattering efficiency, right? So If the size of the disk is exactly the size of the particle, then you have an efficiency of 1. It's as if that particle was an absorbing disk. But that efficiency can be less than, it can be less effective. It can actually be more effective. Actually, the maximum scattering efficiency you can have is actually 2. And I can refer you to appropriate references to tell you how that comes about. I won't get into that here. But mu s, that most of us or many of us are familiar with, is essentially this single scattering cross-section for a single particle multiplied by the number density of those scatterers in the material. So this has units of number per unit volume multiplied by scattering cross-section, which is area, and then you get the units 1 per unit length. Okay? So the reciprocal of mu s gives you the scattering mean-free path for photon travel. So let's look at, so I talked a little bit about how the scattering amplitude matrix gives you the total angular description of scattered light from this particle. So let's look at what these scattering amplitude matrices may look like. So let's look at cases where your scatterer is typically larger than the wavelength of light. This is a simulation or solution of how red light interacting with a water droplet of 10 microns in diameter in air, how it scatters light. So this is a polar plot. It's a polar plot that's logarithmic. So each of these concentric circles represents an order of magnitude drop in your intensity. You see that light is coming from the left to the right. You have this huge forward peak. Most of the light is actually directed completely forward. And then you have a drop in 1, 2, or 2 to 3 to 4 orders of magnitude in your scattered intensity. And you have this very irregular, sharply oscillating features in your scattered light. Does anybody have the common description for why a large particle gives rise to scattering with so much structure? As opposed to Rayleigh scatterers, which we'll see in a moment, has very little structure. Right, so interference of scattered light. So why would you see more interference for a Mie scatterer than, say, for a Rayleigh scatterer? Your answer is correct. So
give a more forward scattering particle, you get more light scattered in forward directions. So interference in that direction.
But we're seeing the structure at other directions, not the forward direction, right? You're seeing the structure. Okay, so good. It's a good answer. And so let's talk about this. So let's think about this conceptually. We have a particle which, and you have this this incident wave that's coming in. And remember, the wavelength is much smaller than the diameter of light. So if you kind of take a freeze frame and you look at the interaction of this wave with this particle, you have this oscillation in, let's use black here. There we go. We can see this a little better. And so this is an oscillation in electric field. So if you think about charges within this particle, depending on where you are in the particle, the dipole has a different orientation, right? So this is moving past. So what you're doing is you're inducing dipoles, right? So here, maybe at this location, the dipoles look like this. Here, the dipoles have the opposite orientation. And of course, and then here again, you have, and all of these guys are oscillating, right? Because this wave is passing through. These dipoles oscillate, and oscillating dipoles re-radiate light. All of these have different phases. So they're all radiating in all directions. You're capturing that scattered light in all directions. And you have all of this constructive and destructive interference because these dipoles all have different phase relationships to each other. When you add them up, you're going to get this chaotic, seemingly chaotic interference structure. Okay? So that's why you have the structure for Mie scatterers. All of this disappears when you go to a Rayleigh scatterer, because basically the wavelength now is huge compared to the scatterer. Scatterer is like that. And so at any given time, the whole particle is basically one dipole. Okay? And so you just have a single radiating dipole. So this is very complicated. There are some useful approximations for the single scattering cross-section. This is a reference that tells you how you can approximate the reduced scattering cross-section for a particle with a refractive index NP, diameter A, lambda is the wavelength, and M is the relative refractive index, the refractive index of the particle relative to the refractive index of the surrounding material. A is the cross-sectional area of that particle. Okay, and so the key thing is that you have, see, I gave you the answer here. It's constructive and destructive interference. So that's why you have the structure. Okay, and then I've already told you that Mie scattering, you won't see the structure. I've shown here a typical Mie scatterer with incident with either parallel polarized light in red or perpendicularly polarized light in S. You see that the scale is linear instead of logarithmic, and you have these very either a lobe structure or perfectly isotropic re-radiation of light. For those of you who are familiar with single scattering anisotropy, which characterizes the forward-directed or backward-directed nature of light scattering, all Rayleigh scatterings have a G equals 0. All Rayleigh scatterers scatter light equally in the forward and in the backward hemisphere. The intensity or the amount of the scattering cross-section essentially is very strongly coupled to the diameter, to the 6th power of the particle, and inversely related to the wavelength to the 4th power. And again, M is the relative refractive index of the particle with the medium. So here the angular distribution is symmetric and varies gently with polar angle. Now, tissue is very complicated, right? Tissue has all of these structures across spatial scale. How do we characterize typically in transport scattering? So in the context of the radiative transport equation, scattering is parameterized through two elements. One is the scattering coefficient mu sub s, and the other is the phase function. And the phase function is essentially the scattering amplitude matrix that you saw a few slides ago, but for being agnostic to polarization, for randomly polarized light. In diffuse optics, where we use, say, the standard diffusion approximation, often what we are interested in is something called the reduced scattering coefficient mu sub s prime. And that is the product of mu s times 1 minus g, where g is something called the single scattering asymmetry or anisotropy coefficient, which is the average cosine of the scattering angle. So g can take on values typically anywhere from 0 to 1. G of 0 is a scatterer that scatters equally in the forward and backward hemisphere. As g goes to 1, it means that you become more Mie-like in the sense that you scatter more and more in the forward direction. So different scatterers can have different values of g. You can imagine a Mie scatterer is 0. So the question is, can someone maybe intuitively just describe why we might be interested in this reduced scattering coefficient as opposed to mu s by itself?
Just if G is closer to 1 and you have mostly forward scattering, then you would have less of an effect from scattering on whether light reaches your detector or not. It would be more as if it hadn't scattered at all.
That's right. So in the limit of G going to 1, it's as if you have no scattering, right? So particles, so you can have a lot of particles in the medium. Mu s would be high, right? Because mu s is the product of the single scattering cross-section times the number density. You can have a high mu s, but if g is high, each individual scattering event is not doing much to deflect the light field that much. Whereas you could have fewer particles that have g equals 0, and they're doing a much more effective job at dispersing the angular directions of the trajectory of light. So this kind of puts particles or systems with different efficacy in dispersing the light on equal footing. Okay. To describe, and since we have a population or a mixture of Rayleigh and Mie scatterers, we also, it's helpful, since a lot of us do spectroscopy, to model the wavelength dependent properties of scattering. Some people use a single power law. Basically, they characterize this reduced scattering coefficient as some lambda to the minus b power, lambda minus some lambda naught, which is the scattering coefficient at some reference wavelength, times some magnitude. You can do a more sophisticated separation and say, well, my tissue has some fraction of Rayleigh scatterers, and we know Rayleigh scatterers decay with this lambda to the minus 4, and it's really the rest of the scatterers, which aren't Rayleigh scatterers, they're Mie scatterers, and they decay with some other coefficient. So this is from a really nice paper by Steve Jacques again a few years ago. And what he's done in this plot here is plotted the B that you get from this functional description of mu s prime versus the more simple single power law, and plotted them on this plot and looked at various pieces of tissue data. Now, if your tissue lies along this 45-degree line where B is equal to B sub me, it basically means that you have very little Rayleigh scattering in that tissue. Because if you, the more Rayleigh scattering you would have, the more this B me will be smaller than the value of B when you just compress or basically try to describe all of your scatterers with a single power law. And then this kind of tells you how the fraction of Rayleigh scattering, if you have more and more Rayleigh scatterers, the difference between B me and B becomes larger. Okay, so the more and more Rayleigh scatterers you have means that the more B me is smaller than B. So you can stare at these plots a little bit and get an understanding of how the relationship of microstructure, what you know about the differences in microstructure of these tissues, how that might relate to a mixture of Mie and Rayleigh scatterers. And then also the total overall magnitude of scattering is highly diverse with different tissue types. The strongest scattering tissues are typically skin and epidermis. The lowest scattering tissues are typically glandular tissues like breast or lung. Okay. And then, of course, we have this, the angular redistribution of scattering can be parameterized by this mean cosine of the scattering angle, the single scattering anisotropy as a function of wavelength. And there are many people who have done experiments looking at how that might have a wavelength dependence. Okay, so let me talk quickly about absorption and then we can close. So absorption is described a little bit differently depending on which kind of community you come from. From a chemical standpoint, often they depict transmission as some optical density, rho, that is raised to the, or 10 to some power, or 10 to some optical density rho, where rho, the optical density, is a product of a molar extinction coefficient, which has units of the extinction per unit concentration in molarity and per unit path length in terms of centimeters. And then you have some concentration and you have some path length. So this transmission is 10 raised to the power of epsilon, this extinction coefficient times your concentration times your path length. This is convenient because if you say you have an optical density of 1, it means that you get about 1/10 of the light out than you put in. If you have an optical density of 3, it means you have 1,000th of the light comes out then going in. So the numbers are easily interpretable. From physical literature, they treat absorption more in the particle context. They think of an absorption cross-section and a number density of absorbing particles. So, and so you have an exponential of this absorption cross-section times number density of absorbers times some path length, and this gives rise to an exponential, it gives rise to Beer's law. And the reason why I wanted to show both of these descriptions is that often in our field, what we use is mu sub A. But if you look in the literature and you want to try and extract an effective mu A, and you're looking in the chemistry literature, you better be careful that they're using log base 10 here, and they're using log base E here. You're going to miss a factor of about 2.3, which can give rise to problems. So you just got to be mindful that there are different conventions. Don't mix your product of epsilon and C. The product of epsilon and C is not the same thing as mu A. Okay, so just be careful. Okay, and again, the reciprocal of mu A, it gives you a basic mean free path for absorption. There are many things in tissue that absorb. Here's a subset of them. Typically, as all of you know, tissue isn't very optically transparent either in the ultraviolet or in the infrared. In the ultraviolet, water actually absorbs a fair bit once you go below 200 nanometers. Proteins and DNA absorb quite a bit. And of course, we're very concerned about DNA absorption in the ultraviolet. That gives rise to skin cancer. Then, as you go into the visible, you have the main players typically are melanin, oxy and deoxyhemoglobin, water, and also fat, which I haven't shown here. What's very interesting, as you all know, is that as you go from orange to red, all of a sudden tissue becomes much, much less opaque because the absorption of blood, whether you're looking at oxygenated or deoxygenated species, plummets by 2 to 3 orders of magnitude. And all of a sudden, you have absorption that's much lower than the typical amounts of scattering in the tissue, and you can penetrate deeply. And then, of course, the party doesn't last forever. Water rears its ugly head around 1300 nanometers, and the window is shut. So you've got this optical window around 650 to 1200. Okay, and water and also collagen rears its head further in the infrared. I like to look at this plot. Maybe it's because I made it, but I think it's very informative if you take the ratio of scattering to absorption and look at that versus wavelength. And so you see the optical window very clearly here. You see these absorption features due to blood, but right around 650, you see all of a sudden the amount of scattering relative to absorption just rises, and then it drops again because absorption of water rears its ugly head. And so this, if you just kind of look at the ratio of scattering to absorption of around 10 as a good metric, you see directly the optical window is basically 600 to about 1100 nanometers. Okay, and this is also important from the standpoint of modeling because, as I said, the diffusion approximation is really good when scattering is dominant over absorption. This will tell you the wavelength band in which you can use the diffusion approximation. And then you'll look at the wavelengths where scattering and absorption are comparable. In those cases, you'll have to use radiative transport in Monte Carlo. Okay, so that's really important to bear in mind. And then, as I promised, there's this interaction, this interplay between the characteristic length scales for light transport and the characteristic spatial scales in tissue. I think I'm going to, since I've run over, I'll leave this for you to look at. You're going to see all of these later in this course, especially when the diffusion approximation comes up. We're going to be talking about reduced transport coefficients and effective attenuation coefficients. But typically, there are absorption and scattering wavelength length scales, which are linked to the absorption and scattering coefficients, and there are also time scales because it takes time for light to travel these typical absorption and scattering lengths. So the time scale for absorption to occur is much, much longer than the time scale for scattering to occur in biological tissues. So if you're using intensity modulated sources, you're going to be sensitive to absorption on longer timescales than you're going to be sensitive to scattering. So let me break there. Open it up for, why don't we take a break, and then I'll open it up for questions, and then we'll transition to our next talk. Okay, thank you.